Hello everyone, I am Ripon Kumar Shah and I am presenting our work MetaVIn, Meteorological and Visual Integration for Atmospheric Turbulence Strength Estimation. This was done in collaboration with Scott McCloskey, my intern supervisor from Kitwer, and Shuren Jayasuriya, my academic supervisor from Arizona State University. Let's explain what is turbulence. When you are imaging any object by a sensor in 3D turbulence field in a scale of kilometer distance, light doesn't go straight, it bends, and because of that, what you really see is a 2D distorted image. And it happens because of temperature, pressure, and wind speed fluctuation, and it causes distortion like blurring, image displacement, and scintillation. And what you will see seems something like this. This is pretty common when you see a twinkling star or distorted view across hot summer road. We used prior dataset to train and evaluate our model. Those dataset comes with weather data as well as images data. Those weather data include temperature, wind chill, heat index, dew point, relative humidity, wind speed, wind direction, barometric pressure, and solar loading. We can get those dataset from any weather station, cost around $100. However, score estimation is really expensive. We need to set up both receiver and transmitter scintillometer miles away and need to align them together. That might take hours. Also, they cost around $100,000. Those prior dataset were collected around different parts of USA from November 2021 to January 2023, and they were collected across different seasons and different places. We have included BRS 1.1, BRS 2, BRS 3, and BRS 4. Those 4 datasets were used to train our model, and we tested our model on BTS 3 and BTS 4 dataset. Sharpness is one of the important metrics for image degradation estimation, because when the turbulence strength is high, usually images get degraded. Also, sharpness value decreases a lot. So we explicitly compute sharpness metrics in 3 different ways and take their magnitude. Those include sharpness in terms of Laplacian, tangent grad, and variance of gradient. We have used CAN in our model for score estimation. CAN is Kolmogorov-Arnold network. The Kolmogorov-Arnold representation theory was originally proposed by Andrei Kolmogorov and Vladimir Arnold. It is different from MLP because MLP has fixed activation function and learnable weight. However, in case of CAN, they have learnable activation function, which is approximated by B-spline network, and their edge weight is fixed. The Kolmogorov-Arnold network was released on May 30 of 2024, and it has shown the power to approximate MLP with only 1% of the parameter. And this is a visualization of feature importance when we use CAN with different weather and image-based data. So we found that on the right side, temperature, wind chill, and solar loading are the most important parameter for score estimation. Also, distance is quite important. So basically, the distance of scene from camera is considered important when we estimate square. Beside, the variance of gradient, tangent grad, sharpness, those are also considered important. Now on the left side, if you see that when the temperature is negative, we see more square. However, in wind chill and solar loading, usually positive value tends to come with higher square. So this is the score estimation architecture. We get the mean, which is the scene to the camera distance, and those are already included in a bright dataset. From a single frame, we compute the sharpness, tangent gradient, as well as the variance of gradient. Also, from nearby weather station, we get different weather data, including temperature, wind chill, heat index, dew point, relative humidity, wind speed, wind direction, barometric pressure, and solar loading. And then we provide all those values to the Kolmogorov-Arnold network, and we train that to predict CN square. For baseline comparison, we have used image quality based assessment for CN square estimation, because they can also compute the degradation of the images, and CN square also do the degradation. We found that when we apply image quality based assessment on a single Briar dataset, those are not that bad. However, when use them across the whole dataset, their prediction is pretty bad. The some top performer include Park to Peak with 0.14 of correlation coefficient and Music with 0.09. However, in most of the cases it is pretty bad, and in some of the cases the correlation comes out negative. However, in case of MetaVIn, we get pretty good accuracy. For example, when including sharpness and distance only, the correlation is not that good. When you include only meteorological or weather data, the correlation gets pretty much better. When including meteorological, distance as well as sharpness value from images, the correlation is the same as the CAN only using meteorological data. The last approach that combine meteorological, sharpness and distance in CAN, which is MetaVIn, we get the best accuracy with mean absolute value of 0.17, a significant drop from 0.24. So let's inspect one of the scene. The top row show one scene, and we're only inspecting one of the sign there. From the left to right, we have CN square increasing about 1-fold each, or 10 times. So from the left to the last one, we have about 1000 times CN square increasing. And on the bottom side, we are showing the CN square in logarithmic format. So the first scene have pretty low CN square, and because of that it is pretty sharp, and the temporal standard deviation is pretty low because it's not fluctuating a lot on the time domain. So you see that the ground truth and prediction value is pretty aligned. The second scene show kind of similar system, so the standard deviation is slightly higher, and the third one is a lot high, and in all those three cases CN square is pretty aligned as well. The last one, because of high CN square value, the images is already degraded with very less sharpness, so we also see lower temporal standard deviation here. However, in most of the cases, ground truth and prediction is pretty aligned. Also, it shows the power of MetaVIn at different situations. For example, in snowfall, low contrast, motion blur, overexposure, haze, or perfect illumination, our ground truth versus our prediction is pretty aligned without a big fluctuation or jump. And we can see more visualization here from different parts of the time and days, and from different cameras with black and white, as well as very noisy images and images with a lot snowfall. However, in most scenario, the ground truth and prediction are mostly aligned. We have some of the failure case as well, shown on the bottom right situation. However, those are in exponential format, and this is only a maximum 2 times difference, which is pretty negligible, because in case of scintillometer as well, if you just compare one ground truth scintillometer to another ground truth scintillometer, they can also go up to 60% off. And those are some of the benchmark results, where if we see that classical image quality assessment or deep learning based image quality assessment are not that great, with very low Spearman correlation or very high mean absolute error. In case of recent one like gradient CN score estimation, those are also not that robust. If you use transformer or efficient net version 2 model, those are pretty robust here, with Spearman correlation of 0.3 or 0.7 for efficient net version 2. MetaVIn achieved a superior result of 0.93 with mean absolute error of 0.17. So it shows that MetaVIn outperformed all other approaches by a large margin. So to conclude, MetaVIn with camera weather station setup as shown on the bottom right can achieve comparable result to very expensive $100,000 scintillometer with only 1% of the cost, with greater accuracy that generalize across different scene, environmental, and temporal conditions. The research was supported by National Science Foundation, Director of National Intelligence, IARPA, ACU Research Computing, and thanks to Rodi, Brandon, and Daniel from Kitor for helping me access the broad dataset. Visit our project page for more details about MetaVIn.